significantly different than identity matrix. So naglibog kita. An identity matrix just has one along the main diagonal and the zeros in all other places. So in other words, it's a matrix where variables are not correlated whatsoever with each other, but as always, a variable correlates 1.0 or with itself. So it has ones and a mean diagonal zero, so everywhere else. So the fact that this is significant and it's extremely significant, the p-value is very small here. It gives us the confidence that our variable are significantly correlated. So once again, these testing whether the variables are a set or as a set, does this matrix or does this group of variable differ significantly from all zeros here? And it definitely does. So that's what the test measures. Okay, next we have here our commonalities, and I'm going to skip over that for a minute. Okay, let's go back that soon. Okay, let's go to total variance explained. Okay, so we'll also pull up our scree plot here. Okay, so you have here our scree plot. Kikita ka mga scree plot, guys. Okay, I want to show the scree plot over here. And these two tables here, the total variance explained and the scree plot, both ideal with what's known as our factor extraction methods. And if you recall, when we went through SPSS, the options we left the eigenvalue greater than 1, rule option selected as default, so we also selected that as curry plot to be put output in our analysis. And there are two the most commonly used procedure for deciding how many components or factors to retain. So how many do you want to keep in our solution? Here we have our total variance explained table note. Notice first all five we have your components in our rows here. And you may be wondering, well, wait a second. I thought a factor analysis, the whole purpose of it is to reduce the number of variables, di ba? Pagamayon siya. But if we're thinking like that, insakto siya actually. So, amo na aton purpose. But just a matter of definition, it's always the case that the number of variables we put in our analysis will be equal to the number of components shown here. So, we have five variables input in our analysis. Therefore, we have five rows or five components shown here. Now, here in our initial eigenvalues, table. You can see it here. Notice that we have these various eigenvalues. So the first one is 3.136 and everything after that is less than 1. Now, if you recall, our first rule was eigenvalue greater than 1 rule. So that was keep the number of the factors or components that have eigenvalues greater than 1, and the other components with eigenvalues less than 1, such as these here, for example, we do not keep them. So, kakasan siya. If you look here in the extraction sums as well, of squared loadings section, you will see here that there's only one value here now. And that's what it means. This is how many components SPSS retain or kept based on the rule that we set. So since only one component had an eigenvalue greater than 1, we only have one component in our solution here. So the results of this rule tells us or indicates that we want to have one component lang. So in other words, we reduce those five variables to one variable only. Or that one component from this perspective does a pretty good job at explaining the relationships between SWLS1 to 5. So one way to assess how good of a job this analysis did at explaining the relationships between those variables is to look at the percent of variance accounted for by the component. And this is here, this example, our one component solution accounted for 62%, 62.72% of the variance or about 63 of variance, which is pretty good in practice. Was usually kakita kita between 40 to 60 of the variance in the 40 to 60s in that range. So wala ka tayo usually kakakita sa ibang nga solution ng variance higher than 70 and solution below 40 is not very strong. But that's typically the range that we see them in. So I would say na 63 is pretty good na in practice. So now, an interesting here is recall that we have five components. If you add up these eigenvalues, they will be equal to 5. So within rounding, um, yeah, within rounding error lang. So the sum of the eigenvalues is always equal to the 5, or the number of components, or put another way, the number of original variables in your analysis. So if I had 10 variables in my analysis here, then all the values as well is equal to 10. And in fact, this would be 10 rows in this table. Now, since I have 5 variables, I'm going to have 5 components lang output in my initial solution. And the eigenvalues will be sum up to 5. And the reason why that's good to know is that if you have divide the eigenvalue for our retained component 3.136 over 5, you'll get exactly 6272 or 62.72%. When converted to percentage, so the percent is rounded accounted for. Okay, so in summary, our eigenvalue greater than one rule indicated that one component should be retained. Next, let's look at the scree plot here. So our scree plot, notice first of all that on the x-axis, the component here is plotted. So this is the first component, and the second component, third, and so on and so forth. And on the y-axis, we have our eigenvalue plotted, and this is in fact, if you think about it, this is graph is really just plotting ang aton nga eigenvalue di kagina sa babaw, and component 2 is somewhere between 6.6 and point 0.7. If you look here, we go to sa aton nga between 0.625. So nag-drop siya gamay sa number 3, and nag-drop siya nga little by little up until sa 4 and hasta sa 5. So this tree plot is literally just eigenvalue again plotted from left to right. So now the rule of thumb is interpreting the scree plot, and this is how we interpret our scree plot. So what we want to do here is we want to retain the number of components that are above and what's known as the scree, or where this plot tends to not drop much. So when it tends to, I wouldn't say flatline, but chopper off this very gradually. Notice how these 4 points here, these number 4 values here, rate of change or the slope here is quite minimal as we move across. But at this value, there's a big drop from component 1 to component 2. And then from component 2 all the way to 5, there's not much of a change anymore. So according to the scree plot, we interpret the number of components above where they tend to not change anymore. And where this name comes from is the scree. The scree is a geological term actually, which indicates the rubble or the stones that fall off from a cliff. So if you think of a cliff, you're diving along the road, you're going to see a lot of stones, smaller size rocks and some bigger, but they are all collected along the side of the mountain, right? So this is the scree or the rubble that is collected off the cliff. So that's where this name comes from. So if you want to retain the number of components above to the scree, so the scree plot would indicate to us here that we want to retain one component. So suppose there was a component right here as well. We'll notice that it still drops quite a bit from here to here, and then it flatlines. So if we add component here as well, we would retain two components in the case. So if you add components like likelihood of these two rules of thumb agreeing completely, it decreases. So it certainly can happen. They can agree without question, but the likelihood tends to decrease. So one of the interesting things about these two rules are that the eigenvalue greater than one rule has been around for a very long time and has the scree plot. The eigenvalue greater than one rule was published actually by Kaiser in 1916. That was very old now, but it's still one of the primary methods of extraction for determining the number of components na ginagamit up until today. And the screenplot year, the key publication for that is actually 1966 by Raymond Cattell. So this came out in 66, the publication. So the publication for this came out in 1960 by Kaiser, and that's quite a long time ago. There's still two primary methods that are used for factor extraction. Now, that being said, for those who are interested in more advanced look at factor analysis, there are better methods that we can use, such as parallel analysis. But unfortunately, wala siya sa output ka SPSS. So you can go ahead and run a parallel analysis if maka-search ka mo sa web, or you can use syntax for SPSS to run it, or you can use some websites. So, but really beyond the scope of this video, if I get a chance, I'll try to make a video kaninyo sa parallel analysis, but let's try and look at that lang, ha? Okay, so to review, in our example here, we have one component, and next we'll go ahead and look at our component matrix. And aton rotated na component matrix, di na to siya. Hmm, okay, okay, please wait for a while, guys. Mhm. Okay, so notice it says, no, okay, please wait for a while. Okay, I added na. Sure. Alagay sa danom. So, notice it says component rotated component matrix here. Only one component was extracted and the solution cannot be rotated. And that's a very important point.